Okay, I want to do an example showing the energy mass relation equals gamma mc squared. But before I do that, I want to talk about units because it's really like this is really important. This isn't just a little thing. It's really important to understand how to use these units. It really makes your life a lot easier to do calculations if you understand the, the, the units and how they work. So what I mean by that is let's look at the units of energy, right? What are the units, energy units? Well, you know the joule or the J, and the joule is, right, it's a kilogram, it's MV squared. Yeah, 1/2 mv squared. So kilogram meter squared per second squared. Kilogram times meter squared per second squared. Okay, so that's the unit. I always put units in brackets, right? I want to relate that to the EV or the electron volt. The EV is also a unit, right? I guess that I just wrote 1 EV. EV or electron volt. I guess I could have said joule equals electron volt. That is a unit. And the EV is really easy to see what an EV is. E is the charge of an electron, right? It is literally an E times a volt. Charge of an electron, the charge of the electron is 1.6 times 10 to the minus 19 coulombs times 1 volt. That's what an EV is. And so that gives you 1.6 times 10 to the minus 19 coulombs times volts. That's the unit. And I guess I don't know about brackets here because I'm actually doing some math. I guess we can ignore the brackets because we're really just saying 1 EV is 1 point. So 1 EV, the quantity 1 EV is 1 times 1.6 times 10 to the minus 19th coulombs times 1 volt. So that's sort of a physics equation. And so like I just wrote above, I'm just rewriting it. 1.6 times 10 to the minus 19 coulombs times volts. And what's a coulomb times a volt? A coulomb times a volt is a joule, right? Those are both MKS units of charge and voltage, and charge times voltage is energy. So that's a joule. So it's 1.6 times 10 to the minus 19 joules. Okay, so 1 EV is equal to 1. So this is a conversion factor. 1 EV is 1.6 times 10 to the minus 19 joules. So the EV is just a very small amount of energy compared to the joule, right? And so we talk about joules when we talk about kilogram masses that we're lifting up 1 meter. That's 10 joules of energy. Whereas the EV, where that's more often what we'll use when we're talking about subatomic particles, much smaller masses, right? 10 to the minus 19th smaller amounts of energy. Now, why is the EV, and why do I say this is a really important concept? Well, it's because, let me just write out a couple of other units. So the EV or the joule are both units of energy. What about a unit of momentum? Unit of momentum, right? We never had any particular unit of momentum, but momentum is the kilogram times the meter per second, right? Kilogram meter per second of mass. That's the MKS unit of momentum. That's the mass times the velocity. Well, so a unit of momentum would also be, since energy has units, right? So kinetic energy, for example, is 1/2 mv squared. So energy has units kilogram meter squared per second squared. Then the units of momentum must be the units of energy divided by a velocity, right? So joules over meters per second must also be units of momentum. And so that means that another unit of momentum, a different unit of momentum, must be 1 EV over c. 1 EV over c is a momentum unit, and it's a momentum unit that we use in relativity. Let's just see, because that is a momentum unit because it's an energy over velocity. It's just a convenient momentum unit. And let's just see what that is in MKS units. 1 EV per c, write this a bit better, 1 eV per c, that's a unit of momentum, is equal to 1 times 1.6 times 10 to the minus 19 joules divided by 3 times 10 to the 8th meters per second, which is 0.178 times 10 to, oh, whoops. Oh, no, that's right. I made a mistake, sorry. Which is equal to 0.533 times 10 to the minus 27 kilograms meters per second. Okay, so that unit of momentum, so we've just shown the 1 eV per c, which is unit of momentum that's often used in relativity, is equal to that much kilogram meters per second. And then what about unit of mass? A unit of mass. Unit of mass, well, mass is just the kilogram, right? But the kilogram must also be an energy. Look at the unit of momentum, right? It's an energy over meters per second squared. So joules over meter per second squared is a kilogram. So in relativity, what do you think? A unit of mass is a 1 eV per c squared, is often the unit of mass. If we're not using MKS units, we might use this unit. 1 eV per c squared is 1 times 1.6 times 10 to the minus 19 joules divided by 3 times 10 to the 8th meters per second squared, which is equal to 0.178 times 10 to the minus 35 kilograms. So 1 eV per c squared is a mass, and it's a very small mass. It's 10 to the minus 36th of a kilogram. Okay. So why are these useful units? Well, let's see. Let's look at the mass of an electron. So for example, that says example. The mass of an electron. The mass of an electron, look it up in MKS units, is 9.11, if you don't already know it, minus 10 times 10 to the minus 31 kilograms. Go ahead and convert that to eV per c squared. So 1 eV per c squared over 0.178 times 10 to the minus 35 kilograms. Hopefully you know how to do unit conversions now. So this is just your conversion factor given by this conversion here. And so the mass of an electron in eV per c squared, do out the math, and you get 0.511 MeV per c squared. Oh, what's m? Mega, 10 to the 6th. So it's 0.511 times 10 to the 6th electron volts per c squared. So the mass of an electron is 9.11 times 10 to the minus 31 kilograms, or it's 0.511 times 10 to the 6th electron volts per c squared. Now, why is that useful? Well, it's useful because it's sort of more natural numbers, 0.511. And yes, this is an MeV per c squared rather than EV per c squared. So there's a factor of 10 to the 6th. But it's a more natural number than 10 to the minus 31 kilograms. But why else is it useful? Well, because then we can say, oh, what's the energy? What's the rest energy of an electron? And this is going to be important in relativity. What's the rest energy of the electron? The rest energy of the electron is the mass of the electron times c squared. What's that equal to? Well, if you wanted to go ahead and do 9.11 times 10 to the minus 31 kilograms times 3 times 10 to the 8th meters per second squared equals ... I'm not actually going to write that out because we could instead do 0.511 MeV per c squared. That's the mass times c squared. Oh, look, it's 0.511 MeV. It's 0.511 mega electron volts. That's the rest energy of an electron. So it just makes for easy conversion between masses and energies when we use these units. Makes very easy conversions between masses and energies.